All right, folks, let's go over this word problem over here, okay? So this is basically a word problem that has to do with sine, okay? That has to do with sine and cosine, okay? When you see the word sinusoidal, that means either sine or cosine, okay? Even though you're tempted to think that it's sine, okay? So we're talking about tides right now, okay? So on a particular July 4th in Galveston, Texas, high tide occurred at 9:36 a.m. At that time, the water at the end of 61st Street Pier was 2.7 meters deep. Okay, low tide occurred at 3:48 p.m., at which time the water was only 2.1 meters deep. So we're going to represent this using let me switch up colors here, okay? Using a wave that looks like this, and at the top is 2.7 meters. At the bottom is 2.1 meters, okay, from the information that was given over here and here, okay? And assume that the depth, okay, let me just delete this S over here. Assume that the depth of the water is a sinusoidal function of time with period half a lunar day, about 12 hours and 24 minutes. Okay, about 12 hours and 24 minutes. I want to open a slide over here that, let's see here, I think it was 4.5 or 4.4. I just want to get a slide ready. There it is, okay? So, let's do some quick conversions over here. Let's just get some stuff set up over here. I want to convert the hours and the minutes into a decimal. So 12 hours and 24 minutes, you put it over 60, and that 24 over 60 on your calculator becomes 0.4. So essentially this is 12.4, okay? 12.4. So 12 hours and 24 minutes is represented as 12.4. By the same logic, 9 hours, okay, and 9:36 is represented by this, and as a decimal, that becomes 9.6, okay, 9.6, okay. Similarly, this becomes, by the same logic, okay, 15.8. The reason is 15 is because this is PM, so you got to do 12 hours plus the 3, which gives you 15, okay? Or you can think of it as military time. Okay, so now we have these three, three times converted into decimals, okay? Let me get rid of these highlights over here. Here is our generic function that we're going to use over here, okay? Y equals to, let's see what I used over here. Y equals to A times, times sine or cosine, parentheses B, X plus or minus H, and then plus K. This looks complicated, but is based off something we already know, actually. Okay? Now, when you look at this portion here, that should ring a bell. Those are horizontal transformations. Okay? This piece over here is a horizontal translation, left or right. Think opposite hats. This is horizontal stretch compression, okay? If you move the K over, okay, if you move the K over and do minus K, and then times 1 over A to both sides, so these go away. The K and the A represents vertical transformations. The K is a vertical translation left-right. 1 over A, that's a vertical stretch compression. Okay, so the reason I'm telling you all of this is so that this green thing that seems foreign right here, this green equation that seems foreign is actually familiar because it's basically horizontal vertical transformations. Okay? Now, all right, now our objective for this problem is to basically fill in those yellow highlights with numbers. Okay, and then also choose between sine or cosine. Okay, so let's start easy here. Okay, now if you read this problem, this starts at a high tide. Okay, it starts at a high tide. Now, if you look here, if you look at the sine and cosine function, which function also starts on a high tide? The answer is cosine. Okay, cosine starts cleanly at 0 at a high tide. Okay, so we're going to choose cosine. Okay, we're going to choose cosine here. Okay, let's see if I can change this equation over here to black. All right, and y equals 2. Let's go ahead and rewrite that in black. So we're going to choose cosine here. Okay. Now, if you go back to this here, this high tide starts at 0, and in terms of time in the day, 0 is 12 a.m. Okay, 0 is 12 a.m. Okay, but high tide, according to the problem, started at 9:36 a.m. or 9.6. So really, we need to somehow move this high tide over to 9.6. We need to shift this 9.6 units to the right. Okay, let me say that one more time. We need to shift this high tide 9.6 units to the right. Okay, so to the right means opposite. Remember, to the right, using opposite hats means minus 9.6. And again, I got the 9.6 here, which is the number that's converted from 9:36 a.m. Okay? So right off the bat, we finish H. Okay? All right. Now, for K and A, all right, for K and A, so this is going to be a little bit counter to how I taught this before. Before I said always use opposite hats. We're only going to use opposite hats for H, okay? Everything else is going to be regular hats, and that may seem confusing, but believe me, it's going to be easier in the long run to do it this way. So opposite hats is only for H, everything else is a regular hat, okay? So, so let's do K and A at the same time, okay? Now, if I were to draw x-axis and a y-axis, okay, the middle over here is going to be 2.4, okay? The middle is 2.4. You can just literally on your calculator do find the average of 2.1 and 2.7, which is 2.1 plus 2.7 divided by 2, and you get 2.4, okay? The reason that's important is because I want to take us back to the original function, which looks like this, okay, and analyze it from this standpoint. How many units did the yellow function shift upwards vertically in order to get to 2.4? The answer is 2.4. Let me say that this way. You need to shift the yellow graph 2.4 units up so that the yellow becomes the green graph. Okay, so that is why K is going to be plus 2.4. Okay, now A right here, you can think of it as the height or amplitude. Okay, you can think about it as the height or amplitude, and that is going to be this right here. Okay, I'll do this in white also. This is going to be 0.3. Okay, 0.3. Let me do that point a little better. You can also think about it like this. This is also 0.3 here. However you want to analyze it, from middle to top or middle to bottom, it gives you the same thing. So A is going to be 0.3. Okay? All right, and then we slap on a y equals to here, which leaves us with this B. How do you find B? So we're almost done with this problem. Okay? We're almost done with this problem. We just have to find B now. Now, if you look at the slide that we did last week, okay, period is basically taking this coefficient here. Okay, let's say I erase this. Okay, and we look at, let's pretend it said 4, which is duds here. Let me just do it in red to line up the colors. You take 2 pi, which is a given / fixed number. This 2 pi never changes. Okay, but hold on. Let me back up and explain period. Okay, re-explain period because we did explain it last week. The period of this blue graph is 2 pi because it takes 2 pi units on the x-axis for the blue graph to repeat itself. Let me say that one more time. The period for this blue graph is 2 pi because it takes 2 pi units on the x-axis for the blue graph to repeat itself. By that same logic, the period for this red graph is going to be pi over 2. Okay, this says 0, that says pi over 2, because it takes pi over 2 units on the x-axis for this red graph to repeat itself. Okay, so that, excuse me, that explains the concept of period. Okay, now how do you find period without a graph if there's only a coefficient given to you in front of the x? Let me say that one more time. How do you find period without the graph, without Desmos, if only a coefficient is given to you in front of the x? The way you do that is you take, again, 2 pi, which is a fixed value. Excuse me, you divide it by the coefficient, which in this case is 4. 2 pi over 4 reduced becomes 1 pi over 2. Okay? Let's say this coefficient was 4 over 3. Then you do, again, 2 pi divided by the 4 over 3. You do 2 pi divided by 4 over 3. Keep, change, flip. Keep that, change it from division to multiply. Flip that fraction to 3 over 4. 2 times 3 gives you 6. Invisible 1 times 4 gives you 4. 6 divided by 4 reduces a fraction is 3 over 2. So in this green case, you can ignore this, by the way. Okay? In this green case, all right, you don't have to worry about this right here. In this green case, if 4 over 3 is your coefficient, by this process, you will end up with 3 pi over 2 is your period. Let me say that in terms of the definition of period, which is that it will take 3 pi over 2 units on the x-axis for the graph to repeat itself. Okay? So let's use that same logic here again for the previous problem. Okay? Again, let's repeat the method and the formula. You take 2 pi divided by the coefficient to give you the period. Again, 2 pi divided by the coefficient to give you the period. Let's use the same logic over here. Okay? Let's side hustle B in blue. Okay? So 2 pi divided by the coefficient, which is B, will give you the period, which is 12.4. Okay? And we're trying to find B so that we can plug it in here. Okay? I'm going to divide that by 1. Okay, I mean, it's invisibly underneath. The 12.4 is a 1 is what I meant to say. Cross multiply, and you get 2 pi times 1 equals to 12.4 times B. This times 1 doesn't matter. You divide both sides by 12.4. What you do on one side, do to the other. These cancel. 2 over 12.4 reduces as a fraction to 1 over 6.2 equals to B. Okay, so this gets placed right there. Okay, all right, so I'm going to get 1 pi over 6.2 as my coefficient. Okay, and that is your equation, folks. This equation will model the tides that are described previously in the problem. Okay, now the cool thing with this equation is that, well, the hardest part is actually getting this equation, this function. Once you get it, you can do some cool things with it. Let's say we want to find out what is the tide height. Okay, what is the height of the tide at 4 a.m.? Well, then you just plug in 4 here. What about if we want to find out what is the height of the tide at 1 p.m. in the afternoon? Then you put in 13 here, because you got to think of it as military time. 1 p.m. is really represented by 12 hours that pass by from midnight to noon, plus the extra 1. So 12 plus 1 will give you 13. Okay? If we're trying to find the height of the tide at 11 p.m., then you got to do 12 hours from midnight to noon, plus the 11, which gives you 23. Okay? And if you want to, we can go the opposite way now and use this function in order to find, go backwards. So let's say we know the tide is at 2.5. Okay, let's say, let me phrase it this way. At what time, okay, or let me rephrase it this way. If the tide is at 2.5 meters high, what time of the day does that occur? Okay, what time of the day does it occur where the tide is 2.5 meters high? So you plug in 2.5 and solve backwards for x. Okay, so you do 2.5 minus the 2.4 divided by 0.3, inverse cosine, that's cosine with an exponent of -1 to both sides, and then you multiply by the reciprocal of this blue and then add 9.6. Okay, anyhow, the last two items of plugging in for x or plugging in for y and solving backwards for x, we'll do that another time. I just want to give you a sneak preview. Okay, thank you very much for tuning in, folks. I know that was a long video, but it's actually really not that complicated of a concept. It just has quite a bit of moving parts in it. Okay, thank you for tuning in.